Hello, friends. Welcome back to this uh, uh, topic of electromagnetic composites and their applications. And I am continuing this topic in this session also. So, in the last session, I have discussed these things, requirements for good ME composites and historical background of these ME composites also I have explained. Now we'll see the types of materials, ME materials. That means the magnetoelectric materials. So one type we have, it is single phase ME materials. So single phase ME materials were first invented or studied by the researchers like chromium oxide. Chromium oxide is that it is a single phase material. So first, this magnetoelectric effect is found in single phase materials. But after the study of these single phase ME materials, what is found is that the magnetoelectric coefficient, the magnetoelectric voltage coefficient found in case of single phase materials was very, very less. That is the one problem. And another problem was that these single phase materials were having a very low Curie temperature that was even below the room temperature. So these two problems of single phase materials led to the invention of a new type of materials. They are called as the multi-phase or the composite materials. So to overcome the limitations of single phase materials, now we have the two-phase materials. They are called as the composite materials, magnetoelectric composite materials, and were first proposed by Van Sestelen in the year 1970. So in the two-phase materials, two phases are generally a ferromagnetic material phase will be there, and ferroelectric phase will be there. So these two phases, that is ferromagnetic and ferroelectric phases, are combined together, mixed together to get that one material that is called as the magnetoelectric composite material. The important advantages of these two-phase materials or the magnetoelectric composite materials is that they have the enhanced ME coefficient, that is very high values of magnetoelectric voltage coefficient was found in these ME composite materials. And the working temperature or the transition temperature is also very high. It is beyond room temperature. It is beyond even 100 degrees centigrade, 200 degrees centigrade. That kind of composite materials are available. And flexibility in operational temperatures is an added advantage, and material design, manufacturability, and tailor making properties of these ME, magnetoelectric composite materials, led to the popularity of these materials in the research field. And subsequently, many devices are fabricated by making use of these multi-phase magnetoelectric composite materials. So this graph shows the growth of research field in magnetoelectric composites. So this is obtained from the source Google Scholar. You can see along the x-axis here is plotted, and along the y-axis the number of papers produced during the years. So you can see the exponential growth in the number of papers published on these magnetoelectric composites in the literature. So this is the peak time between the 2015 to 2020. Very large number of papers are reported in the various important journals. And even you can see the number of papers produced is more than 12,000 here is found. So this shows the importance of this magnetoelectric composite materials in the recent science and technology and in various applications. Here I will explain how to prepare the ME composites, synthesis, how to synthesize these ME composites. Different methods are there. The different methods are available for the synthesis of these ME composites. And now here I am explaining, I am showing a flow chart for the synthesis of these ME composites by ceramic technique, or it is also known as the solid state reaction method. So as I have explained in my earlier sessions, we need two phase materials. One is the ferrimagnetic phase, other one is the ferroelectric phase. So both the materials of different phases we have to synthesize. So here on left you are looking at the flow chart for synthesis of a ferrite material. So this is just an example. Lithium magnesium ferrite is chosen here because this lithium magnesium ferrite is having a good resistivity values and a very high Curie temperature. Because of that reason, this lithium magnesium ferrite is chosen as the ferrimagnetic phase. And the ferroelectric phase is barium titanate. This barium titanate is having very good ferroelectric properties. That is why that barium titanate is chosen. And here, how to prepare the ferrite material, this lithium magnesium ferrite is that you have to take the respective oxides or carbonates of the metal ions present in the ferrite material. So for the lithium, you will have to take the lithium carbonate, and for the magnesium, you will have to take the magnesium oxide, and for the iron, you will have to take the ferric oxide. And these three starting materials should be weighed in a high accuracy weighing machine, digital weighing machine, according to the chemical formula, what is used, and the amount of these oxides calculated by calculations. These oxides are to be weighed accurately, and accuracy should be at least 4 digits. Such a balance should be used, and these carbonates, oxides are mixed together in an agate mortar. You will have to use an agate mortar, which is a granite thing to mix these starting materials, and it is not a dry mixing, it is a wet mixing. That means you can use the water as a mixing agent to mix these oxides, or you can use any organic compounds like acetone, glycine, toluene, that kind of highly volatile compounds, liquids can be used as a mixing agent. So what is the advantage of mixing these starting compounds in the organic compounds like acetone is that you will get the uniform mixing of all these compounds, and the acetone gets evaporated easily at a smaller time. But if you are taking water, pure water as a mixing agent, you will have to grind these compounds for a very long time to get a dried fine powder. So that is a problem. So generally, acetone is used to mix these compounds. Then, after mixing these starting materials in an agate mortar, you will have to pre-sinter the compounds. For pre-sintering of these different samples, you will have to use the alumina crucibles, because alumina crucibles are having the withstanding temperature of more than 1200 degrees centigrade. So generally alumina crucibles are used. So you have to keep that ground of fine powder into the labeled crucibles, and crucibles are kept inside a muffle furnace, and pre-sintering will be done generally in this temperature range 600 to 700 degrees centigrade. Temperature is used for pre-sintering, because during the pre-sintering, just the crystallization process just it starts, and whatever the things like carbon, all those things, they get evaporated at this temperature in the form of gas. So that is why around 600 to 700 degrees centigrade should be the pre-sintering temperature, and time will be generally of the order of 10 hours. Once the pre-sintering is done, you will have to take the compounds out of the muffle furnace after they get cooled naturally, and you have to mill. Means again you have to grind that pre-sintered powder for 2 to 3 hours to get a very fine powder. So in this way, you are getting a pre-sintered ferrite sample, ferrite powder. Similar way, this side we are preparing the ferroelectric material, ferroelectric phase, that is the barium titanate you have to prepare. For the preparation of barium titanate by this ceramic or the solid state reaction method, similar method is adopted, but the starting compounds or which are needed to prepare this barium titanate or barium carbonate and titanium oxide. So in the same manner, you have to weigh this barium carbonate and the titanium oxide to high accuracy to the calculated amount, and these two are mixed together in a gate mortar in the acetone medium, and they are ground to get the fine powder until they get dried. That fine powder obtained after mixing of these two barium carbonate and titanium oxide, that mixture has to be again pre-sintered in a muffle furnace. For that, you can use the alumina crucibles and pour this pre-sintered. You pour this dried mixed powder of barium carbonate and titanium oxide into the labeled alumina crucible, and keep the crucible inside the muffle furnace, and the pre-sintering can be done at 700 degrees centigrade for 10 hours. After the pre-sintering is over, when the furnace cools down, you will have to take that crucible outside, and that powder, pre-sintered powder, will have to be again grind into a fine powder. So now we have this side, we have the pre-sintered powder of ferromagnetic material, ferrite, and this side, on right side, we have the pre-sintered powder of barium titanate. And these two, ferrite phase and ferroelectric phase, are now mixed in a proper ratio, like 1:2, 1:3, like that. So at a different molar ratio, these two powders are mixed together, and a final sintering, and again mill and pre-sintered too. That means, if possible, again at for example, let us say 700 degrees centigrade, you can pre-sinter the mixture of this ferrite and ferroelectric phase, and next after that, you will have to press that second time pre-sintered powder into pellet form or the torrid form to carry out the measurements, and some powder should also be there to take the XRD, all those things. So next, here we are making the final sintering of these composites at let us say 1050 degrees centigrade, or even at 1100 degrees centigrade for 12 hours. So once the final sintering is over, we have obtained AME composite materials here. So here, in this way, we prepared the ME materials by this ceramic or the solid state reaction method. So another method of synthesis of composite materials is there. So that is the auto combustion method. This is the new method of preparing the materials, and this is a very simplest, and it takes very less time, and the powder obtained here is of nano range. The powder what you are obtaining at the end is a nano material, whereas the powder what you are obtained in case of ceramic technique is not a nano material. The particle size will be in the micrometer range, but the powder prepared by making use of this auto combustion method will be in the nano range. So here you are getting a nano ferrite. So to synthesize the this nickel copper ferrite, just an example, by combustion method, what are the things you need is that you need the nickel nitrate solution and copper nitrate solution and iron nitrate solution as the three metal nitrates, and then these are called as the oxidizers, and you need a fuel to burn these three metal nitrate solutions, and for that this glycine is used as a fuel. So you have to make two solutions, one in two separate beakers. In one beaker you are actually in three beakers. In three beakers, you have to prepare the calculated amount of nitrate solution, the calculated amount of copper nitrate solution, and calculated amount of iron nitrate solution in three beakers. Let us say you can prepare in 100 ml beakers these things, and next they are transferred into a beaker of some 500 ml, and they are mixed thoroughly. And this is one end. On other side, this glycine solution should also be prepared in a 1000 ml beaker. In a 1000 ml beaker, a glycine solution should be prepared. Then this mixture of this metal nitrate solutions, which in a 500 ml beaker, and now that solution, that mixed solution is poured into this glycine solution in a 1000 ml beaker, which is a fuel. So now here all the solutions are mixed together. That means metal nitrate solutions and the glycine is mixed together. Here the beaker should be at least 1000 ml beaker, otherwise because once the burning starts, the burning solution comes out of the beaker, so that is the very dangerous thing, or even it may come or rush out suddenly, it may expand, so that may take place. So that is why you have to take 1000 ml, at least 1000 ml beaker to mix all these things. So all these things are mixed here, and that beaker is and pH you have to check at this stage. It should be around 7. If it is not around 7, you can add some ammonia to bring that pH back to the 7. And now nitrate to glycine solution is 1:2. That means the concentration of the fuel should be very high, double of the concentration of the nitrate solutions. And now this mixture of the solutions of metal nitrates and glycine, which is present in a 1000 ml beaker, is kept on a heating bath on a hot plate, which is having 200 degrees centigrade. And after some time, so what happens? The combustion of the solution, mixture solution present in 1000 ml beaker starts burning. It catches the fire. Generally, the burning takes place for 2-3 minutes, not more than that. So in that time only, everything gets burns off, and a huge fumes or the gas, blackish gas also comes out. So you should be careful that you have a proper exhaust in the laboratory, otherwise it may damage your health. So here you are getting the burnt ash of this thing after combustion, and this burnt ash, when it cools down, you have to pour everything into the agate mortar again and grind it, and it is a very fine powder, you are getting, and this fine powder can be calcined or precipitated at 500 degrees centigrade just for 4 hours, and again once again grind it, and here you are getting nickel copper ferrite powder of which is in the nanoscale. So you are getting a nanoferrite here. You are getting a nanoferrite here. So the time which takes place to get a nanoferrite, nickel copper nanoferrite, could be a total of 2 to 3 hours. In 2 to 3 hours, you can prepare or you can obtain the nano nickel copper ferrite powder. But this is not possible when you are using the ceramic technique. To prepare the sample by ceramic technique or the solid state reaction technique, at least 2 days are required. So that is the problem. And the powder obtained by the ceramic technique is also not in the nano range. But here, the advantage of this auto combustion method is that you are getting a very, very fine powder, and the time used to synthesize the compounds is also very, very less. So that is the biggest advantage of this auto combustion method. And nowadays, most of the researchers use this auto combustion method to prepare the different composite materials or some other materials. So similar procedure, this is the procedure what I have explained is for synthesis of this ferrite phase only. So same procedure you have to adopt for the synthesis of this piezoelectric phase. So next, in the next session, I will explain these things, the types of connectivity. What are the meaning of these types of connectivity? We will see in the next session. Thanks for listening.